Picture this. You're scrolling late at night, snack in hand, and up pops a dramatic headline about a cosmic visitor slipping through our solar system and turning the sun into a drama queen while rattling the ground under our feet. It reads like space filed for a restraining order against common sense, but it is also wildly compelling because the story has everything we love: mystery, danger, and the secret hope that the universe is sending us a personalized push notification. Earth is basically a rock that won the cosmic lottery, and when a rumor claims that a stranger from deep space can stir our star and shake our cities, the jackpot alarm goes off in our brains. Before we rush to conclusions, let us talk about why this kind of rumor sounds so believable. First, there is scale. A comet has presence. It carries the mood of an ancient omen with a modern digital makeover. Our storytelling instincts love a simple chain. Visitor arrives, sun acts weird, Earth trembles, boom, we have a plot. Second, there is timing. If any natural event happens close to a headline, our minds glue them together. It is like hearing a car alarm and instantly blaming the cat. Third, there is novelty. Interstellar visitors are rare, and rarity makes any coincidence feel loaded with meaning. We are pattern hunters. Give us a new dot, and we will draw a constellation around it before breakfast. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure. Only if you enjoy these calm journeys through the universe. Now, let's begin. Now, I know what you want from this chapter. Not an answer, but a reason to keep listening. Consider this your invitation to an experiment in careful wonder. We will keep our feet on the ground and our eyes on the sky. We will let excitement breathe, but we will ask it to show identification at the door. We will say yes to curiosity and yes to questions, and also a strong yes to evidence. Think of this as a guided tour through two neighborhoods, the world of how things actually work and the world of what if. We will not treat them as enemies. We will enjoy the thrill of speculation and then hold it up to the light like a gem, looking for cracks and sparkle. Let us also set the tone right now. There will be jokes, because science without a smile is a missed opportunity. Photosynthesis is plants saying that they invented solar panels first. Black holes are the universe's way of deleting browsing history permanently. And gravity is basically the universe whispering, "I like you. Please come closer," but in a very clingy way. Humor is not disrespect. It is an invitation. When we laugh, we relax, and when we relax, we learn better. Here is the promise of this episode. We will not rely on spooky vibes. We will not chase every dramatic word that starts with inter and ends in panic. We will build a clean path. First, we will understand what this visiting object actually is and why it is interesting on its own, without the extra drama. Then, we will tour the sun's natural mood swings, the kind powered by magnetism and motion inside the star itself. We will take a calm look at earthquakes and remind ourselves that the ground moves for very down-to-earth reasons. We will test the rumor the way a good lab would test a glowing potion from a fantasy market, with patience, with measurements, and with the awareness that shiny bottles can hold ordinary soup. Before we go deeper, let us untangle a favorite storytelling trick, the great cosmic domino. The rumor says visitor nudges sun throws a fit, Earth gets a headache. It sounds neat because it is linear, but nature often runs more like a 1,000-player improv scene than a single-file line. The sun has cycles born from its own restless interior. Earth has plates that drift like slow-motion continents on an invisible conveyor belt. Space weather and ground weather each have their own recipes. You can put these things next to each other on a timeline, and your brain will throw confetti, but confetti is not a diagnosis. There is also the problem of scale. A rumor can treat the solar system like a tiny mobile hanging over a baby crib, where the slightest breeze makes every part wobble. In reality, this mobile is massive, layered, and stubborn. The sun is not a delicate wind chime. Earth's crust is not a loose floorboard. And a comet, even a charismatic one, is not a cosmic remote control. We will respect the thrill of possibility, but we will not hand a pocket flashlight the job of turning off a lighthouse. So why keep watching if the likely answer is probably not? Because this is not only about debunking, it is about upgrading your curiosity. When you learn how rumors gain traction, you sharpen your ability to enjoy wonder without getting fooled. You become the friend who can keep the excitement while steering the conversation back to reality. You learn how to appreciate a comet as a messenger from another star system without assigning it superpowers. It does not need to be fascinating. You become the person who can say, "That is an amazing story. Let us check what the data would have to say." Before we leave this opening chapter, let us draw a small map for the road ahead. We will meet the visitor with fresh eyes. We will learn what it takes to move the sun's needle. We will talk about the real reasons the ground shakes and how to be ready in the real world. Rumor or not, we will explore thoughtful what-if scenarios, not because they are true today, but because they teach us to think clearly about tomorrow. And we will end with a grounded verdict that respects both our sense of wonder and our responsibility to reality. If that sounds like your kind of ride, buckle up. Curiosity is the engine, evidence is the seatbelt, and the view out the window is the best part. One more smile before we continue. Somewhere, a plant is quietly turning sunlight into dinner, like a smug little chef, and our star is busy being a giant fusion bakery with zero need for outside drama to keep working. The universe is amazing, even on a normal day. Let us enjoy that truth while we chase the next chapter. Chapter 2, Meet the Traveler, what 3I/Atlas is, and where it came from. Let us meet our guest properly, without the fog machine. 3I/Atlas is the label for an interstellar visitor, which means it is not a native of our solar neighborhood. It is a wanderer from somewhere beyond the reach of our familiar planets, carrying the fingerprints of a different birthplace. Think of it as a tiny envoy from a star we do not yet know well, passing through our town square, glancing at the clock tower, and continuing on without buying a souvenir. Interstellar objects do not stick around. They arrive on paths that do not close into loops. They swing by, tip an invisible hat to the sun, and vanish back into the dark. If comets were house guests, local ones bring luggage and stay on and off forever. Interstellar ones leave the engine running. The name tells a tidy story. The letter and number at the front mark it as the third interstellar object ever confirmed, after two earlier celebrities that changed how we think about small bodies between stars. The survey name at the end points to the project that spotted it. Atlas is a sky patrol that scans for moving specks of light, the same way your eye catches a firefly in a field, because it shifts against the steady glow of the grass. Night after night, the survey compares pictures of the same patch of sky. Fixed stars stay put. A traveler drifts. Find the drifter, measure how it moves, and you can sketch a path. The path for an interstellar object is not a bound loop like a planet's orbit. It is more like a one-way highway exit that never curves back. So what is this traveler made of? We cannot hold it in our hands, but we have clues. Interstellar comets likely carry a familiar mix of rock and frozen materials, such as water ice and carbon dioxide ice, built long ago in the deep freeze, far from a young star. In those cold zones, grains collected into pebbles, pebbles into boulders, and boulders into bodies. Some of those bodies were tossed around by the giant planets that were still finding their seats at the table. Every developing star system is a little bit chaotic, the cosmic version of a family moving into a new house with boxes everywhere. During that rearrangement, some small worlds get flung out entirely. Most wander forever between stars, quiet and unseen. A rare few aim just right to pass through another star's domain, and every once in a while, that domain is ours. When one shows up, astronomers cheer the way birders cheer for a species that almost never lands on this continent. Yes, it is still a chunk of rock and ice, but it is a chunk with a passport stamp from somewhere else. Earth is basically a rock that won the cosmic lottery. Meeting a rock from another lottery is a bonus round. How do we tell for sure that a visitor is truly interstellar? The key is the shape of its journey. If you map the motion with careful observations, you can tell whether the path loops around the sun or whether it opens out like a trumpet flare. A bound path means it belongs here. An open path means it came from the outside and will not be staying for dessert. Astronomers confirm this by tracking the position night after night and running it through models that ask, given this motion, what path fits best? When the answer is an open road rather than a closed ring, you have a traveler from afar. There is something quietly poetic about that. The proof that it is a stranger is the fact that it refuses to be captured. Where could it have begun its story? Picture a young star wrapped in a wide disk of gas and dust. Inside that disk, countless tiny collisions and mergers build planetary seeds. Big newborn planets, especially the massive ones, throw their weight around. They nudge, tug, and sometimes eject smaller bodies, like impatient bouncers clearing a dance floor. The ejected bodies do not vanish. They become the unclaimed luggage of the galaxy, sailing between star systems for ages longer than the entire written history of humans. Our traveler is likely one of those castaways, sculpted in a distant nursery, fired from its home by the rough diplomacy of gravity, and now crossing our path by chance. The galaxy is full of such cast-offs. We notice only the few that wander into the glow of our sun and become bright enough to see. What can we learn from it? Even a brief visit lets telescopes sniff out the dust and gas released as sunlight warms the surface. Those materials carry chemical stories. They are like a recipe card from another kitchen. How much water? How much carbon dioxide? How much of other familiar and unfamiliar ingredients? If those proportions differ from what we find in local comets, that tells us that planet building in other systems can follow different rules. If the proportions look similar, that tells us that nature likes to reuse a good recipe. Either way, we learn. Science is generous that way. Even a null result is a gift with a bow on top. Black holes may be the universe's way of deleting browsing history permanently, but comets are the universe's way of leaving sticky notes all over the place that say, "Here is how I cooked this." There is also the question of size and surface. Interstellar travel is rough. Tiny grains impact over long ages. Heat from passing close to stars can crust the surface. Some parts may be darkened by organic-rich residues baked by radiation, while fresh patches may pop open when sunlight warms trapped gases, and a jet of material blows off like a microscopic geyser. To observers, that outgassing can look like a faint tail or a hazy coma around the object. To storytellers, it looks like personality. This is not just a rock. It is a traveler with breath. Finally, there is the quiet thrill of the clock. Interstellar visitors move quickly relative to our planetary tempo. They brighten for a short season, then fade. That urgency focuses the global astronomy community. Telescopes in different countries trade time, techniques, and notes, like a relay team handing off a baton through the night. The goal is simple: capture as much truth as possible before the curtain falls. When the traveler leaves, the data remains, and with it, a sharper picture of how worlds form and wander. That is the heart of this chapter. 3I/Atlas is not a monster, not a cosmic switch, not a harbinger. It is a messenger. It arrives with a story in its dust, offers a few pages to read, and then heads back into the dark corridor between the stars. If that is not worthy of attention, I do not know what is. Chapter 3: What it takes to stir the sun. How our star actually behaved. If you want to know whether anything can ruffle the sun, you first need to understand what the sun is doing all day long. Spoiler: it is busy. Our star is not a sleepy campfire. It is a layered, boiling, magnetic powerhouse that writes its own weather. Imagine a colossal engine room wrapped in light. It does not need outside drama to get excited. It brings its own fireworks. Black holes may be the universe's way of deleting browsing history permanently, but the sun is the universe's way of saying, I run the server, and the server is always on. Start at the center, where the sun earns its glow. In the core, matter is packed and hot enough for fusion to turn tiny building blocks into slightly heavier ones, releasing energy as if the star were a bakery that never closes. That energy does not zip straight to the surface. It spends a long, wandering life as it bounces around the radiation zone, a thick inner layer where light plays the slowest game of pinball ever invented. From there, the energy reaches the convective zone, and that is where the soup really starts to boil. The convective zone behaves like a pot of thick stew just about to bubble over. Hot material rises, cools near the surface, and sinks again. This churning carves the photosphere, the visible surface, into a quilt of tiny bright cells called granules. Each granule is a plume of hot gas rising, a bright fleck with a darker edge where cooler material sinks. Step back in your mind's eye, and you see a planet-sized field of sparkle. The surface is never still. If Earth is basically a rock that won the cosmic lottery, the sun is the casino that paid out the prize money and then kept the lights blinking forever. But rising and sinking is only half the story. The sun also rotates, and it is a strange kind of rotation. The equator spins faster than the poles, a behavior called differential rotation. You can picture this like a giant orange made of syrup. The middle turns more quickly, while the top and bottom lag behind. This uneven spin, combined with the endless boiling in the convective zone, acts like a cosmic egg beater for magnetic fields. Lines of magnetic force get stretched, twisted, and sometimes knotted. When the tangles become intense, the sun vents its frustration. That venting is what shows up as sunspots, flares, and, on a really dramatic day, a coronal mass ejection that heaves a cloud of charged particles into space. Sunspots are cooler, darker regions shaped by magnetic fields that clamp down on convection, like traffic police telling rising hot gas to take the long way around. They march across the surface in groups and drift in latitude over time. If you keep a careful diary, you find that sunspots wax and wane in a cycle that lasts a little over a decade. Early in a cycle, spots appear at mid-latitudes. As the cycle matures, they creep toward the equator. At the same time, brighter regions called faculae lace the surface near spots, and towering loops of glowing plasma arch over the limb. To casual eyes, it is pretty. To scientists, it is the heartbeat of a magnetic engine. Under the surface, there is a thin, critical boundary where the smooth flow of the inner radiation zone meets the choppy sea of the convective zone. Many researchers think this boundary, often nicknamed the tachycline, is the control room for the solar dynamo. Here, differential rotation shears magnetic fields into new configurations. A common picture, named after two scientists, the Babcock and Layton model, suggests that surface magnetic fields decay and slide toward the poles, get wound up by rotation, and then re-emerge as new active regions in the next cycle. You do not need the full math to appreciate the elegance. The star recycles its own magnetism, like a blacksmith endlessly reshaping steel. We know these hidden flows exist because the sun rings like a bell, waves ripple through its body, and by measuring the tiny up and down motions of the surface, a field called helioseismology maps the interior. It is like listening to an instrument and deducing its shape from the tones. These measurements reveal belts of faster and slower flow, giant convection cells larger than continents, and a slow river of material that creeps from the equator toward the poles at the surface and returns deeper down. That river, called the meridional circulation, helps carry magnetic fields around the star, setting the stage for the next act. Then there is the upper atmosphere, the corona, It is bafflingly hot compared to the visible surface beneath it. Magnetic fields thread the corona like glowing scaffolding. When those fields snap or reconnect, they fling energy outward, and the sun releases flares that briefly outshine whole regions and coronal mass ejections that loft enormous clouds into interplanetary space. Space weather forecasters track these outbursts because they can buffet the bubble of magnetic field around our planet, sparking auroras and, in rare cases, stressing our technology. The key point is that these events are homegrown. They are the product of tangled magnetism born of rotation and convection. The sun is not a polite guest waiting for outside invitations to throw a party. It is the host. So what would it take to truly stir the sun? Imagine trying to influence a raging ocean by tossing a pebble from a cliff. Unless you are standing on a cliff the size of a small planet, and your pebble is secretly a moon, the ocean will not notice. To budge this star's magnetic engine, you would need influences comparable to its own deep flows and fields. The sun already moves to the rhythm of forces, vastly larger than anything a passing object could provide from a distance. It is not fragile. It is not a wind chime that rings when a stranger walks by. It is more like a stadium full of drummers who cannot hear a single tap at the door. That does not make the sun boring. Quite the opposite. The wonder is that one star can produce so many patterns from such basic ingredients: rotation, hot fluid, and magnetism. It is a masterclass in self-organization. The next time you see an image of loops arcing over the solar limb, or a time-lapse of spots parading across the face, remember that you are looking at a living system of physics, a dance choreographed by the star itself. And if you catch yourself wondering whether an outside visitor could push this dance off-beat, smile and picture the sun shrugging kindly. "Thanks for the concern," it would say, "but I already brought the music." Chapter 4, Gravity Reality Check. Why distant objects do not puppet our planet. Let us give gravity its due without giving it a cape. Gravity is the quiet rule-maker of the cosmos, more librarian than action hero. It keeps order by setting gentle but firm expectations. Big things attract, small things follow, and everything dances to the tune of distance. If you remember only one picture from this chapter, make it this. Shine a flashlight at a wall and walk backward. The light spreads out and fades. Gravity behaves in a similar way. The farther you are from the source, the weaker the pull becomes, and it weakens fast. That is why distant objects, no matter how dramatic they look in headlines, do not sit behind the curtain pulling strings on Earth. Mass and distance are the two big characters in this story. Mass is how much stuff there is, the measure of how serious an object is about making other things pay attention. Distance decides how much of that seriousness you actually feel. A mountain right next to you has a tiny tug you would never notice, while a star across the gulf of space might as well be whispering from another room. Gravity may be the universe's clingy acquaintance, but over long ranges, it becomes the world champion of personal space. This is why the usual suspects that influence Earth are either very close, like the moon, or very massive and still relatively near, like the sun. The moon shapes our ocean tides, because it is right there, sharing our neighborhood. The sun rules our orbit, because it outweighs everything else in the solar system by an almost comedic amount. A visiting comet that is small and far away is simply not in the same league. If a house cat strolls past a freight train, the train does not swerve. There is another useful picture. Imagine Earth as a very attentive dancer, with a few long-term partners. The sun is the principal partner leading the big steps. The moon adds a gentle sway, and the giant planets add subtle background rhythms that unfold over many years. A visitor darting across the ballroom might cause a moment of interest, but by the time the music reaches your ears, that guest has already left the floor. Momentum matters. Earth is heavy, fast, and already in a stable groove. You do not change that with a passing glance. What about tidal effects from something flying by? Tides are not about simple pull. They are about difference in pull across a body. Stretch a rubber band more on one end than the other, and you get a shape change. For a distant traveler to create a meaningful tide on Earth, it would need either a very large mass or a very small distance. Distant and small does not pass the test. It is like trying to stir a pot from the next room with a straw. Consider the hierarchy of influence that keeps the solar system tidy. The sun dominates the center. The giant planets shape the fates of countless small objects through patient nudges, not dramatic slaps. Those nudges are most effective when repeated over and over on predictable schedules. That is how resonances work. A small push delivered at just the right time for many cycles can add up. A passerby without a repeating appointment cannot build that kind of cumulative effect. Gravity rewards persistence more than bravado. There is also the question of direction. Even if a newcomer had a non-trivial pull, the effect would not automatically line up with anything we care about on Earth. Forces in space are vectors with directions in 3 dimensions. But you do not need the math to get the idea. If you push a spinning top in a random direction for a moment, the top wobble changes slightly, and then the top keeps spinning. Earth is a very large, very stable version of that top, locked into relationships that have been refined over billions of years. Quick tugs do not make puppets. They make minor temporary adjustments that dissolve into the background. The stability of orbits is another underappreciated protector. Earth does not freewheel through space. It glides along a well-established path defined by the balance between forward motion and the sun's pull. To change that path in any lasting way, you either need a push that is both strong and well-aimed, or many small pushes delivered with perfect timing for a very long time. A visiting object on a one-time flyby offers neither. Think of a river that has carved a canyon for ages. Tossing in a pebble does not reroute the water. What about the notion that a distant object could indirectly cause trouble by stirring the sun first and letting the sun pass along the ruckus? That is a different chapter's debate, but the short, gravity-only answer is the same. The lever arm is too long and the lever is too light. The sun is a self-driven engine. External gravitational tweaks from small, far visitors are the ghost notes of the symphony, not the drum solo. A helpful real-world comparison is the tug from Jupiter, the heavyweight of the planets. Jupiter can nudge asteroid families and shape comet paths over time because it is enormous and it sticks around. Even then, those effects are gradual and mostly concern small bodies that are already easily pushed around. Earth notices Jupiter's presence on long schedules, the way you notice the slow drift of seasons, not the way you notice a door slamming. If the champion of planetary mass delivers its influence like a long poem, a modest passerby recites a haiku and leaves. There is wisdom in that scale story. It reminds us to keep awe and arithmetic in the same room, even when we are avoiding actual numbers. The cosmos is full of beauty and surprise, but it is also full of boundaries that keep the show from turning into chaos. Distant, lightweight visitors do not seize the steering wheel of Earth. They wave from afar, and our world keeps driving. If gravity had a social network, distance would be the privacy setting that keeps casual acquaintances from rearranging your furniture. So the reality check is simple and satisfying. Gravity is powerful, but it respects distance. Puppetry requires strings that reach and hold. In space, those strings thin out quickly. Our planet's main partners are already known and already close. Everything else is background music. Lovely to hear, not in charge. Chapter 5, Earthquakes. In plain words, plates, stress and release. Think of Earth's outer shell as a patchwork quilt of stiff plates floating on a warm, slowly moving layer beneath. The quilt does not sit still. It drifts, edges bumping or sliding past each other over long stretches of time. Where those edges meet, the planet stores strain the way a bent ruler stores springy energy. When the grip along a break finally gives, the ruler snaps back and the ground shakes. That is an earthquake in one sentence. Locked edges, rising strain, sudden release. Geologists are basically therapists for stressed rocks. Let us zoom in on those edges, better known as faults. A fault is simply a crack where two sides have moved relative to one another. The motion is not polite. The surfaces are rough, snagged by tiny rock teeth. Pressure from inside the planet keeps pushing, but friction keeps the teeth interlocked. Over time, stress builds. Then, like Velcro peeled in a rush, the teeth let go and the rock blocks jump. That jump sends waves through the ground. You do not see the fault teeth, but you feel their breakup. Faults live in different neighborhoods. Along convergent boundaries, one plate bulldozes into another. Sometimes, the heavier ocean floor slides beneath the lighter continent and dives into the deep interior. That dive zone locks and releases in big events that can lift seafloors and, in certain cases, shove water to make far-traveling waves. Along divergent boundaries, plates part ways and magma creeps up to make new crust, with gentle shakes as the system breathes. Along transform boundaries, plates grind side by side like two books rubbing on a shelf. That sideways motion is a champion at producing frequent, sometimes sharp shocks. The takeaway: different edges, different styles of stored strain and release. Now, about the waves. When a fault slips, it launches two main types of motion through the rock. The fast ones are compression waves that push and pull the ground in the direction they travel, like sound moving through air. The slower ones are shear waves that shake the ground side to side. When these reach the shallow layers, they feed rolling surface waves that can be the real troublemakers for buildings. None of this requires fancy symbols to appreciate. Imagine a stadium crowd. A chant is like a compression wave, shoving forward and back. A crowd doing the wave is like a shear wave, lifting and lowering shoulders side to side. By the time the motion reaches the upper seats, the whole stadium sways. People often ask, can weather trigger earthquakes? Wind and rain can influence landslides, and heavy rainfall can change pressure in the shallow ground. But the big releases along major faults are driven by deep forces and long-term plate motion. Another favorite question: do small quakes prevent big ones? Not exactly. Small shakes release strain in tiny patches. If the stuck section is large, the big release can still happen later. Think of picking at a zipper that is jammed. Little tugs may move some teeth, but the stubborn section remains until the right pull clears it. Then there are aftershocks and foreshocks, two words that sound like spoilers. A foreshock is simply a smaller event before the main slip. You only know a quake was a foreshock after a larger one happens. Aftershocks are the fault's way of tidying up as the crust settles into a new arrangement. They can go on for days or months, depending on the size of the main event and the complexity of the fault network. The schedule is not a countdown clock. It is a messy negotiation among broken rocks. Can humans cause earthquakes? In a limited sense, yes. Activities that change pressures deep underground, such as injecting large volumes of fluid, can trigger slips on existing faults that are already close to failure. These are usually moderate in size, but can still be felt. It is less like inventing an earthquake from scratch, and more like tapping a wobbly stack of plates that was already leaning. Good monitoring and regulation can reduce this risk. What about volcanoes and earthquakes? They are cousins, not twins. Volcanoes are about molten rock rising and gases escaping, which can crack surrounding rock and create small to moderate quakes. Major tectonic earthquakes, the ones that reshape regions, mostly live on the big plate boundaries and long, ancient fault systems. A volcanic tremor is the rumble of a pot lid rattling. A tectonic event is the countertop itself shifting. The science of measuring earthquakes has grown into a global listening network. Instruments, called seismometers, record motions so tiny that a cat walking nearby could, in the wrong place, become a very confused data point. With many instruments working together, scientists can triangulate the location, depth, and size of a rupture and map how fast and how far different parts of the fault moved. By watching how waves slow down or speed up through different rocks, researchers also build three-dimensional pictures of the crust, which helps locate hidden structures and understand future hazards. Early warning is not prediction. No one can tell you days ahead that a specific fault will snap at a specific time. What early warning does offer is a few precious seconds between the first fast waves and the more damaging slower waves. In those seconds, trains can brake, surgical teams can pause, elevators can open at the nearest floor, and people can duck away from shelves and glass. A few seconds is not drama in a movie. It is enough to save lives in the real world. Preparedness turns knowledge into safety. Strong building codes, smart land use, and simple household steps do more for public safety than any rumor ever will. Secure heavy furniture. Know how to shut off utilities if advised. Practice the classic drill, drop, cover, and hold on. If you live on the coast in an area with risk from ocean waves after a large offshore quake, know your route to high ground and practice it. None of these steps requires a crystal ball. They require steady attention and community effort. Finally, a myth we can retire with a smile. Earthquakes are not Earth throwing a tantrum at people who forgot to recycle. They are the natural consequence of a living planet that moves, rearranges, and cools over geologic time. Fault lines are Earth's way of saying, boundaries are complicated. Our job is not to scare ourselves silly. It is to understand the rules, respect the risks, and build wisely. Curiosity makes the world interesting. Preparation keeps it standing. Chapter 6: The Tide Test. Tiny tugs versus big forces. If you want a clean way to separate cosmic hype from daily reality, run what I like to call the tide test. The idea is simple. If something out there is really pushing Earth around, you should see it nudging the oceans in a clear, measurable way. Water is the world's biggest tattletale. It rises, it falls, it complains to every shoreline twice a day. If an outside guest was secretly yanking our planet, the oceans would rat them out before breakfast. Earth is basically a rock that won the cosmic lottery, and the oceans are the shimmering confetti that never quite lands. So what actually sets the rhythm of the tides? First chair in this orchestra is the moon. Because it is near and not shy about it, the moon creates two bulges, one facing the moon and one on the far side. As Earth spins through these bulges, coastlines feel a repeating rise and fall. The sun plays second chair, adding its own broad, steady pull. When the three players line up, the ocean's range grows larger. When they are at right angles, the range mellows. You do not need equations to feel it. Walk a beach for a week, and you will learn the pattern with your shoes. But the story is not only about sky geometry, it is about geography, which is where the plot gets spicy. Bays, inlets, and continental shelves can amplify or dampen the motion. Some coastlines are shaped like giant tuning forks. When the ocean's natural slosh time matches the timing of the tides, the water stands higher and lower than an open sea. Think of a bathtub that likes to rock at a certain pace. A small nudge at just the right moments sets up a big sway. That is why one harbor might see modest tides, while another, with the same moon and sun overhead, sees epic vertical journeys. The moon may be the original influencer, but local topography runs the fan club. Under your feet, the planet itself flexes a little each day. These are called solid Earth tides. The crust lifts and settles by amounts too small for a casual stroll to notice, but precise instruments measure the motion. Even the air responds. Atmospheric tides ripple through pressure and wind patterns, guided by sunlight and the daily heating cycle. Put it all together, and you get a planet that breathes in many layers, gently and constantly. The ocean does yoga twice a day, the crust does micro squats, and the sky hums along. Now for the detective part of the tide test. Because instruments track sea level and pressure around the world, we have a living map of how the oceans move. If a newcomer in the sky were adding a meaningful tug, we would expect to see a distinctive fingerprint in those records, a new timing, a new bulge pattern, or a repeating swell that matches the newcomer's path. This is not guesswork, it is daily practice. Mariners, coastal communities, and satellites all depend on accurate tide predictions that blend the known lunar and solar signals with local resonance and weather. Any extra puppet master would stand out like a kazoo in a string quartet. There is a tempting misunderstanding here. People hear that a faraway object has gravity and imagine it pulling the whole Earth the same way, like grabbing a suitcase handle. Tides are pickier than that. What matters is the difference in pull from one side of the planet to the other. That difference falls off very quickly with distance. It is why the nearby moon, though modest in size, outperforms the distant sun in shaping ocean tides. Distance is the quiet rule that keeps the show orderly. Gravity may be clingy, but it respects long walks. To appreciate the scale of tidal power, look around the solar system. When a large world hugs a massive planet closely, tides can become world-changing. Jupiter's moon Io is constantly kneaded by the giant next door and erupts like a volcanic fountain show. Europa and Enceladus are warmed by similar flexing, likely hiding oceans under ice. Those are cases where the tiny tugs are not tiny at all, because the moons are close and the parent planets are heavy hitters. The result is dramatic. Cracked ice, heated interiors, plumes that whisper about hidden seas. Tides can be gentle dancers or relentless sculptors, depending on distance and mass. On Earth, ocean tides are powerful enough to shape coastlines, stir nutrients, and challenge engineers, but they live within a predictable budget. Weather can pile water higher through storms and pressure changes, which is why storm surge is a different beast from normal high tide. One is the metronome of the heavens, the other is the drummer of the atmosphere slamming the cymbals. Coastal planners learn to listen to both. There is also a hard boundary to keep in mind, a cosmic sign that says, do not hug too close. Get extremely near a massive body, and you cross a threshold where tides can pull things apart. Rings around planets are partly built from bits that never settled into a single moon, because they orbit inside that no-embrace zone. It is a dramatic reminder that tides are not decoration, they are structure. All of this gives the tide test its strength. We know who the regular players are and how they sound. If a newcomer tries to join the band in any serious way, the rhythm section of the oceans will change. Tide gauges would whisper the news to us within days. Coastal calendars would shift. Satellite altimeters would pick up the new beat. Instead, what we see is a patient and familiar pattern governed by the near moon, the steady sun, and the shapes of the basins they move. So when a rumor claims that a distant passerby is secretly puppeting Earth, ask the ocean first. Has the daily choreography changed? Are harbors rising higher for no local reason? Is the global tide map humming a new tune? If the answers are no, then the tide test has spoken. Water does not lie, at least not about gravity. The oceans will happily spill the tea, then clean it up again 6 hours later. Chapter 7, Space Weather Basics. Flares, winds, auroras, and what actually affects Earth. Space weather is the daily mood of near space, and it matters because our technology lives there. Satellites, power lines, radio links, and even airline routes all share the same invisible neighborhood shaped by the sun's outflow. If regular weather is clouds and raincoats, space weather is charged particles and magnetic fields. It does not soak your socks, but it can make your phone map hiccup, your flight reroute, and a satellite feel like it slept on a lumpy pillow. Think of it as the world's most glamorous forecast. Fewer umbrellas, more auroras. Black holes may be the universe's way of deleting browsing history permanently. But space weather is the sun's way of sending read receipts to everyone with a solar panel or an antenna. Start with the solar wind, a steady flow of charged particles escaping the sun all the time. It is not a hurricane. It is more like a constant breeze with personality changes. There is a slower wind that drifts from regions where field lines loop back, and a faster wind that streams from open corridors called coronal holes, where material can flow outward more freely. When a lane of faster wind catches up to the slower wind ahead, the two streams pile into one another and form a long interaction zone that can buffet Earth for days. Imagine highway traffic where a sports car pack merges into a lane of Sunday drivers, and everyone gets grumpy for 100 million miles. Layered on top of this steady outflow are bursts. Solar flares are sudden flashes of energy from tangled magnetic fields near active regions. They pour out light across a broad range of wavelengths in minutes. That flood can disturb the highest layers of Earth's atmosphere on the daylit side, making high-frequency radio signals fade or drop. If you've ever tuned a radio and heard it hiss for no obvious reason, space weather can be that mischievous neighbor turning the volume knob. Then come the big throws. Giant clouds of plasma and magnetic field launched into space, known as coronal mass ejections. Picture a massive bubble leaving the sun and expanding as it travels. Not every bubble aims for our planet, and not every one that aims arrives with teeth, but when a strong one reaches us, the orientation of its embedded field matters. If it couples well with Earth's magnetic shield, energy and particles pour into the near space environment. That is when the night sky can light up in color and engineers start sipping stronger coffee. Earth is wrapped in a magnetic cocoon called the magnetosphere. It is squashed on the side facing the sun and stretched into a long tail behind us. Most of the time, this shield guides charged particles around the planet like a rock diverting a stream. During active periods, the outer boundary shakes, currents strengthen, and energy gets stored in the long tail until it snaps and flings material back toward Earth. Some of that energy feeds belts of trapped particles that encircle the planet. These belts can swell during storms, raising the risk that satellites passing through will take extra radiation hits, like sailing through a sandblasting booth that suddenly turned the dial to spicy. Now to the headline act for the human eye. Auroras. When space storms funnel charged particles down along magnetic field lines near the poles, those particles collide with the upper atmosphere and excite oxygen and nitrogen. As the atoms and molecules relax, they glow in shades of green, red, and purple. The result is a living curtain that shimmers across the sky. It feels like the planet is holding a neon parade. People sometimes ask whether auroras mean danger on the ground. Usually, they mean wonder in the sky. The real hazards are mostly for technology that operates in the air and in orbit, and for long power lines that stretch across continents. Speaking of power lines, one of the less glamorous but very practical effects of strong space weather is the slow, unwanted electric currents that can be induced in long conductors at Earth's surface. These currents can stress transformers in power grids, prompting operators to manage load and watch for overheating. Pipelines can experience faster corrosion during active periods as well. It is not the stuff of cinematic disaster, but it is very much the stuff of overnight emails that keep grid engineers from getting a full 8 hours. Navigation and communication systems are another sensitive group. Satellite navigation depends on radio signals passing through the ionosphere, a high layer filled with charged particles. Space weather changes that layer's density and structure, which can bend signals in quirky ways. The result can be position errors or temporary outages, especially near the poles and during strong events. High-frequency radio, which many aircraft use on polar routes, can fade during solar flares, pushing flights onto lower latitude paths. That means longer travel times and more fuel, not because the pilots are nervous, but because the sky is temporarily a bad listener. How do we know when to brace? A global network of spacecraft and ground stations watches the sun and the space between the sun and Earth. Solar images track active regions and coronal holes. Coronagraphs see the big bubbles leave the sun, monitors floating upstream from Earth. Sample the arriving wind in real time, giving forecasters a warning window ranging from minutes to an hour. Agencies, such as the Space Weather Prediction Center of the National Oceanic and Atmospheric Administration, and partners around the world turn those measurements into alerts and practical guidance. It is a bit like watching river gauges upstream to know when a town might see high water, except the river is invisible and occasionally glows green at night. What can people actually do with this information? Satellite operators can switch modes, delay risky maneuvers, or harden systems. Astronauts can take shelter in better shielded parts of a spacecraft. Airlines can reroute long flights away from regions where communication would be unreliable. Power companies can balance load and keep an eye on sensitive hardware. For most of us on the ground, the impact is indirect. Your maps still work, your lights stay on, and your aurora photos suddenly get 1,000 likes. Here is the comforting bottom line. Space weather is a real, measurable influence with clear fingerprints and well-tested playbooks. It is not a cosmic mood ring that swings wildly because a random visitor passes by. It is an ongoing relationship between our star and our magnetic bubble, with occasional fireworks and plenty of practical steps to manage the show. If regular weather is storm clouds and sunshine, space weather is the quiet wind of charged particles and the drumbeat of magnetic energy. Both are worth forecasting. One wets your jacket, the other paints your sky. Chapter 8. The Claim on Trial. Could this visitor change solar behavior? Let us run this like a courtroom drama. On the stand, a visiting interstellar object with a bright tail and a mysterious backstory. The charge, altering the behavior of our star. The jury, everyone with a telescope, a laptop, or a healthy sense of curiosity. The goal is not to dunk on wild ideas. The goal is to ask the only question that matters in science storytelling. By what pathway could this possibly work? If there is no credible pathway, then the headline is just a glittery costume. Earth is basically a rock that won the cosmic lottery, and good odds come from understanding how the game is actually played. First, the prosecution's favorite exhibit is scale. The sun is a self-running furnace wrapped in magnetic weather. A passerby that wants to change solar behavior must do more than stroll past the front gate. It must couple to the engine somehow. That coupling would need a mechanism to move energy or twist fields inside the star's outer atmosphere in a way that is both sustained and significant. Think of trying to change a symphony by waving a napkin near the balcony. The orchestra will continue to play because the music is being written by the players on stage, not by drafts in the upper seats. So what are the mechanisms people imagine? One idea is a direct magnetic handshake. The visitor's tail contains charged particles and dust that interact with sunlight and the solar wind. Could the traveler's own magnetic environment dock with the sun's field lines? Like two magnets clicking together? Tempting. But here is the sober view. A comet's magnetic bubble is carved from the surrounding solar wind itself. It is small, fragile, and constantly being reshaped by the larger flow. It is more like a feather on a river than an anchor on the riverbed. Any local coupling is quickly swept downstream. You might stir a tiny eddy in the flow, but you are not rewriting the current of the river. Another proposal is material input. Perhaps the visitor sheds so much gas and dust that upon diving sunward, it feeds the outer atmosphere and tips it toward fireworks. This is a cinematic image. The star slurps a snack and belches a flare. The reality is that the sun sees a drizzle of dust and gas all the time from many sources, including ordinary comets. That drizzle is part of the background diet. For a single object to supply enough extra seasoning to change the recipe, it would need to contribute on a scale that dwarfs typical inputs and do so in a way that aligns with regions already primed for outbursts. That is like tossing a single spice into a cauldron the size of a city and expecting every diner to taste the difference. What about shock effects? The visitor moves fast and plows through the solar wind, creating a small bow wave in front of it. Could that wave travel back to the star and kick the outer layers? The solar wind is an outward flow. Disturbances carried by that flow move away from the sun like ripples on water moving downstream from a paddle. In other words, the paddle is the sun, and the canoe is everything else. A small canoe does not create a wake that runs back upstream to jolt the paddler. There is a subtler idea that sometimes sneaks into podcasts: the butterfly effect. People hear that the sun's magnetic field is complex and imagine that any little nudge could cascade into something major. Chaos is real in nature, but it is not a blank check. Chaotic systems can be sensitive to starting conditions and still be robust against tiny external nudges, because the energy stays inside the system's own boundaries. The sun's cycle is a marathon runner powered by internal stamina. A passerby waving a tiny flag from the sidewalk does not change the runner's pace. Suppose someone insists there was a flare or an eruption, not long after the first photos of the visitor appeared online. That is when the courtroom needs rules of evidence. The sun is active by nature. There will always be an eruption to point to somewhere on its surface during a lively season. To make a real case, you would need to show a pattern of changes that line up with the visitor's path and timing in a way that consistently rises above chance. You would also need to demonstrate a physical connection, not just a calendar overlap. That means predictions. For example, if the visitor could influence a certain sector, then we should see a specific kind of brightening track that sector and fade when the visitor moves on. If the claimed effect appears everywhere and anywhere, that is not a signature, that is numerology with a sunburn. How would a convincing signature actually look? You would expect localized, directional behavior near the part of the outer atmosphere, magnetically connected to the region of space the visitor currently occupies. You might see faint distortions in solar wind measurements, shaped like a consistent footprint that repeats as geometry changes. You would expect the effect to scale with how much material the visitor releases and how close it travels to the sun. Most importantly, you would demand that the same analysis, applied blindly to intervals with no visitor, does not produce the same signal. Any test that lights up equally on ordinary days is a mood ring, not a detector. There is also the three-letter word that keeps big claims honest: cost. What would the sun have to spend to respond noticeably to an outside pebble? It would have to rearrange energy that is already in motion inside its magnetic fields. That happens all the time on its own schedule. Hitching those rearrangements to a new clock requires a coupling strong enough to pull the timing away from that schedule. If you see no change in the usual relationship between the star's active regions and its established rhythms, then you are watching the house band, not a surprise guest solo. None of this makes the visitor dull. It is still a remarkable messenger from a faraway nursery, and its interaction with the space around it is a rich laboratory for studying how small bodies breathe in sunlight and ride the solar wind. But as for changing the behavior of our star in any meaningful way, the case is weak. The courtroom doors swing open, the defendant tips an icy hat, and the judge gently reminds the gallery, fascination does not require superpowers. The sun writes its own weather. Our traveler writes a postcard. Both are worth reading, and neither needs to forge the other's signature. Chapter 9: History's Pattern Traps, Famous Comets and Human Coincidence Hunting. Humans are world-class dot connectors. Give us a night sky, a handful of bright visitors, and a few dramatic earthly events, and we will sketch a storyline faster than you can say, previously on the cosmos. The impulse is ancient and understandable. We want the universe to speak in headlines. Comets arrive with theatrical flair. Tails, glow, sudden appearances. They feel like announcements, but history shows that our love of patterns often outruns the facts. Sometimes we are not discovering a message. We are doodling one. Take the long celebrity of Halley's Comet. For centuries, it showed up and people draped it in meaning. In the medieval imagination, a bright comet could be a royal omen. A crown slips, a bright smear streaks the sky, and the two get braided together in memory. By the time Edmund Halley did the tedious work of comparing old observations and correctly predicted the comet's return, the real lesson was clear. The sky had a schedule, not a mood. Still, the pattern trap lingered. When the comet returned in the year 1910, the world had newspapers, telegraphs, and more nerves than wisdom. Some sellers hawked special comet pills and bottled air, as if the tale were a breath you could catch. Earth is basically a rock that won the cosmic lottery. It does not need a gas mask for celestial confetti. Fast forward to the 90s and the era of Comet Hale-Bopp. It was big, photogenic, and visible for a long time. The sight inspired art and community gatherings, which is the healthy side of wonder. It also sparked fringe claims and a tragic cult story that pinned human fate to a misread light in the sky. The lesson is not that wonder is dangerous. The lesson is that wonder without guardrails can be steered by anyone with a megaphone. Gorgeous objects in the sky do not assign homework on Earth. They just shine. Sometimes the pattern trap leans on timing. A large earthquake happens near the time a comet brightens, and our storytelling brain whispers, aha. But the world is full of overlapping clocks. Major quakes occur every year. Bright comets are not nightly events, but they are not once in forever either. If you circle every natural disaster on a calendar and every bright comet on another, some circles will overlap just by the law of busy calendars. The trap springs when we treat a coincidence as a cause. Another pathway into the trap is selective memory. We are very good at remembering the hits and forgetting the misses. People will fondly recall the time a comet rose and a king fell, but they will not swap stories about the countless nights when a comet rose and nothing in particular happened. That is confirmation bias in a cloak of stars. It is the same reason a friend swears a lucky shirt controls the score. Wins get remembered, losses get folded to the back of the drawer. History also shows how easily records can be edited by fear. In ancient chronicles, a bright visitor might be described in language that already assumes meaning. A sword in the sky, a sign of woe, a dragon's breath. Poetic phrases are beautiful, but they smuggle in conclusions. Later readers, hungry for a narrative, take the metaphor at face value and connect it to plagues, famines, or wars that were already brewing for human reasons. It is like blaming a streetlight for the arguments that happen beneath it. Then there is the tilt of availability. Events that are vivid and recent feel more common than they really are. If a comet arrives and the news is full of volcanic ash, we overestimate any link because both images are striking. But striking does not mean linked. Black holes may be the universe's way of deleting browsing history permanently, yet even they do not tidy up our mental search results when a flashy pairing shows up. We still click the wrong story. A favorite modern pattern trap mixes science words with wishful thinking. You might hear that comets contain organic molecules and leap to the idea that a particular comet must be sprinkling life on Earth right now, or that a comet's tail contains gases that will drift into the air we breathe in a dangerous way. These claims sound official until you ask how the material would actually reach the ground in meaningful amounts. Most of the time, the amounts involved are tiny compared to everyday earthly sources, and the delivery paths are not what rumor suggests. The sky is not a seasoning shaker with a human label. To be fair, not every historical comet myth is gloomy. Some stories are full of hope. People have wished on comets, named children after them, or used them to mark new beginnings. That is lovely. The trick is to let the human meaning be human, not physical. If a comet inspires you to start a project, great. The comet did not tilt your life. Your decision did. Comets make good mirrors. We project onto them what we already carry. So how do we avoid the trap without losing the fun? We borrow a habit from good detectives, build the timeline, then ask for the mechanism. If two things happen close together, pause and ask how one could realistically cause the other. Look for independently gathered data that would have changed your mind if it had pointed the other way. Check whether the claimed pattern survives when dates are shuffled or when the same test is run on random intervals. If the effect only exists when you frame it just so, you are looking at a scrapbook, not a physical law. In short, History is a gallery of beautiful visitors and eager imaginations. The visitors keep arriving, the imaginations keep inventing links. Our task is not to scold wonder, it is to give wonder a compass. Enjoy the glow, take the photo, write the poem, and then, when someone whispers that a comet steers empires or shakes fault lines, smile and ask, by what path? When the path fades under inspection, the story can still be worth telling, as a tale about ourselves, the pattern-making species that finds meaning in the stars, and sometimes forgets to look for the strings. Chapter 10: How Scientists Would Test the Idea. Data, timelines, and controls. If you want to know whether a passing traveler can change the sun's behavior, you do not wave at the sky and wait for vibes. You build a testable story, gather clean data, and try your very best to prove yourself wrong. That is the scientific superpower. It is less about being right and more about refusing to be easily fooled. Think of the process as a courtroom with strict rules, a calendar with honest dates, and a control group that keeps everyone humble. Comets may be the paparazzi of the sky, but science decides whether any of those flashes actually matter. Step 1. Frame the claim. Turn the headline into a clean, testable sentence. For example, during a specific window around the traveler's closest approach, the sun shows an increase in flare counts, stronger outbursts, or unusual radio brightness compared with similar windows when no traveler is present. That single sentence hides a lot of careful choices. Which window, which measurements, which thresholds count as unusual? Every decision must be set before you look at the outcome. If you change the rules after seeing the results, you are not testing, you are decorating. Step 2. Choose the yardsticks. Solar behavior can be measured in many independent ways. You might track the daily number of flares by energy class, the rate of coronal mass ejections, the brightness of the corona in extreme ultraviolet light, the standard solar radio flux index near a wavelength of about 11 centimeters, and the counts of high-energy particles measured near Earth. You could also include maps of magnetic complexity on the sun's surface, produced from magnetograms, which are essentially pictures of magnetic layout. Pick your yardsticks in advance, write them down, and promise not to keep adding new ones until something looks spicy. Step 3. Set the timeline. Define a primary window when any influence would be most plausible. Maybe that is a span of days around the closest approach, combined with an allowance for the time it takes for any disturbance to reach Earth. If you are using instruments near our planet as witnesses, then define flanking windows before and after, and several matching windows in entirely different months when nothing special is happening. These are your controls. They answer the question, what does normal look like? Without that, everything looks dramatic in hindsight. History is great at telling stories. Timelines are better at telling the truth. Step 4. Create the control worlds. Controls come in two flavors. The first is temporal, the same sun during similar seasons of its cycle, but without a visitor. The second is synthetic, shuffled or resampled versions of the data that preserve the overall rhythms but erase specific dates. If the signal you claim shows up just as loudly in the scrambled worlds, you have fallen in love with a phantom. Correlation without a credible mechanism is astrology without the cool graphics. Step 5. Blind yourself a little. A good trick is to mask the calendar labels while you try different analysis methods on simulated data. You only unmask the real dates once the method is locked in. This prevents the human brain from leaning toward the answer it secretly wants. Our minds are charming storytellers and very unreliable referees. Step 6. Test for a lead or a lag. If you think the traveler could influence the sun, you should specify whether the supposed effect should come before, during, or after the closest passage. Then run clean lead-lag checks. Slide one timeline against another and see if any peak appears at a sensible offset. If you find a bump only when the offset is whatever value makes the plot look pretty, that bump belongs in a scrapbook, not a journal. Step 7. Do not cherry-pick geography. The sun is a globe. with regions that spin into and out of view roughly every 4 weeks. If you claim a change, check whether it appears across the full disk and over repeated rotations, not only in a single attractive patch. Also compare with data from spacecraft that watch the sun from different vantage points when available. A real pattern is not shy. Step 8. Count the tries. If you test 20 measurements across 5 time windows, with 3 offsets each, you have made many attempts to find a blip. Some blips will appear by accident. Scientists correct for this by adjusting how strong a blip must be before calling it convincing, or by splitting the work into 2 halves, one to explore, one to confirm. It is the research version of measure twice, cut once. Step 9. Bring in independent witnesses. A change in the sun should leave fingerprints in the solar wind near Earth, in global magnetic disturbance indices at the surface, and in auroral activity at high latitudes. These witnesses should agree on timing and intensity. If only one witness is excited while the others nap, you probably have noise, not news. Step 10. Replicate, preferably by people who disagree with you. Release the data, the code, and the choices. Invite a team that is skeptical to rerun the whole pipeline. Robust results survive friendly fire. Fragile ones dissolve in the first drizzle of doubt. Science is not a popularity contest. It is a stress test. What a positive result would require. To claim success, you would need a change that is specific in time, consistent across multiple yardsticks, visible against controls, and large enough that 2 independent teams recover it using the same locked rules. You would also need a plausible pathway that does not break what we already know about solar physics. In other words, the story has to fit both the data and the playbook of how the sun actually behaves. What a negative result means. If the timelines refuse to line up, if the controls look the same as the supposedly special window, or if the signal vanishes under masking and replication, the verdict is simple. The idea did not survive contact with reality. That is not a failure. That is progress. The universe does not owe our hunches a standing ovation. It owes us the chance to ask well and listen carefully. And that is the heart of it. Testing this claim is not about being a cosmic killjoy. It is about being a trustworthy narrator. When we keep pre-planned rules, honest calendars, and sturdy controls, we get to enjoy wonder without wandering. The sky can stay gorgeous, our analysis can stay grounded, and when we do find real surprises, we will know they are treasures, not tricks, because we made it hard for ourselves to be fooled. Chapter 11. What if one? A closer than expected pass. Imagine the alert comes in at dawn. Updated tracking suggests our interstellar traveler will skim closer than forecast. Not alarmingly close, but close enough to move the event from pretty postcard to history book footnote. No doom, no end credits, just a rare chance to watch an outsider brush past our front porch. If curiosity had a fire alarm, this would be a pull-the-lever moment. The public headline says, closer pass. The scientist translation is, opportunity density just went through the roof. Earth is basically a rock that won the cosmic lottery. Sometimes the prize is front row seats. The first ripple would be the observing playbook. Telescopes around the world would reshuffle schedules, swing open domes, and call in extra eyes. A closer pass means brighter views, sharper spectra, and a better sniff of the gases and dust coming off the nucleus. Observatories would chase the object across different wavelengths, visible light for structure, infrared for warmth and composition, ultraviolet for energetic fingerprints. Radar teams would try for an echo if the geometry allowed, because a radar ping turns a distant smudge into a shape with texture, picture going from a silhouette at sunset to a portrait with laugh lines. Next up is the dust question. A nearer brush increases the sunlight that warms the surface. Warmth frees trapped gases, which push out dust grains like tiny lifeboats launching from a ship. That dust does not vanish. It lays down a trail along the path. Weeks or months later, Earth's orbit might intersect a thin slice of that trail. If that happens, we could get a new meteor shower, a brief signature in the night as grains vaporize high above us. Most would be pinpricks of light that end in a sigh long before they approach the ground. Sky watchers would cheer, kids would make wishes. Somewhere, a pet would look unimpressed and go back to sleep. A closer pass also sharpens our chance to study the way sunlight reshapes a small world in real time. Jets of gas can act like tiny thrusters. The objects spin, can change, surfaces can crack, and in some cases, fragile chunks can fracture and drift away in a family of fragments. That is not a cosmic explosion. It is more like an old log on a campfire, splitting with a quiet pop as it warms. If fragments appear, we get a laboratory in miniature, multiple pieces with shared origin, but slightly different responses to sunlight and the solar wind. Comparing them is like reading multiple pages torn from the same ancient book. Communicators would have a busy day. Closer always sounds scarier than it is. So clarity becomes a lifeline. Agencies would publish easy maps and plain language updates that show where the object will appear in the sky, when it will be brightest, and what it does not do. It does not change tides. It does not shake the ground. It does not press a secret button on the sun. It does offer a chance to step outside and point at a moving piece of another star system. That is the sort of family memory that ends up in holiday albums for years. Satellites and spacecraft teams would check their to-do lists. A closer pass can slightly thicken the local environment along the object's route with extra dust. Most satellites are nowhere near the path, but mission control rooms are professional warriors. They would verify that pointing modes, heater settings, and lens covers are ready if needed. Space is large, the risk is small, but small is not the same as ignore it. Good engineering is a friendship with checklists. In the upper air, a very bright display could nudge the thin layers of gas, a whisper through absorbed sunlight. But that will not rewrite the week's flights. Pilots might mention the view to passengers on night routes. Photographers on dark highways would pull over, set tripods, and discover that car headlights are the true enemy of science. If the tail grows long, people in cities could spot it through the glow, which is a rare public gift. Most of astronomy hides from street lamps. A close comet is bold enough to strut under them. Culture would do what culture does: make playlists, memes, and bedtime questions. Someone would name a cocktail after the object. Someone else would worry aloud that it means fate has opinions. Teachers would slide the topic into class with two magic ingredients: a live sky event and a simple way to help. For example, they could join a citizen science effort to sort images, measure the changing brightness, or flag tiny jets in the tail. When a million eyes become a single instrument, small details stop being small. Scientifically, the crown jewel is composition. With more light to work with, we can pick out subtler ingredients in the glowing cloud around the nucleus and compare them with local comets. If the ratios are familiar, that hints that planet building across star systems follows similar recipes. If the ratios lean odd, that hints that other nurseries bake planets with different spice racks. Either way, we learn space rarely sends us a multiple-choice test with a single correct answer. It sends us essays, and this would be a longer one than usual. There is also the long view. A closer pass tightens the uncertainty on the orbit, and by extension, on the original launch conditions from its birth system. With better trajectory data, modelers can rewind the object's path and set constraints on how fast it was kicked out, what sorts of gravitational shoves it likely felt, and how long it wandered between stars. That turns a single snowball with a tail into a breadcrumb pointing toward planetary weather in a place we may never see directly. Finally, the human piece. Nights like this are invitations. We step outside, we tilt our heads, and for a moment, the daily scroll slows down. Photosynthesis is plants saying they invented solar panels first. A close comet is the sky saying, please look up from your notifications. No apocalypse, no secret switches. Just a rare traveler skimming close enough to make our neighborhood feel both bigger and more connected. If the pass is closer than expected, the story does not change from wonder to worry. It changes from footnote to chapter, and we get to write it together. Chapter 12, What If 2? Dust and Gas in the Inner System. Picture the inner solar system as a largely invisible haze of motes, a slow river of grains, and traces of vapor spiraling around the sun. Most days, it is background ambience, like dust motes in a sunbeam you only notice when you pause. Now imagine our interstellar traveler striding through that room and quietly shedding more grains and gas than expected. Not a catastrophe, not a snow globe shake, but enough to fatten the river for a season. What changes, and who would notice first? Start with the sky itself. Long after sunset, in very dark places, there is a faint wedge of light called the zodiacal glow, sunlight scattered off interplanetary dust. It looks like a ghostly pyramid, leaning up from the horizon. A generous delivery of new grains can tip that glow a little brighter and a little broader for a while, especially along the traveler's path. Sky photographers who chase faint things would be the first to whisper, comparing exposures and noticing that the same camera, lens, and settings need a touch less time to reveal the wedge. It would not dazzle casual eyes in bright cities, but in deserts and mountaintops, the sky would be holding a subtler lantern. Add to that the possibility of fresh meteoroid streams. Dust released along the traveler's track does not vanish, it lines the route like breadcrumbs. Over months to years, some of those crumbs drift under gentle forces and spread into ribbons that Earth might cross. The night show from those grains is not fireballs every minute, but a brief sprinkle of quick, fine streaks with a shared direction. Meteor observers would set up radio antennas that hear the tiny trails of ionization as pings, a kind of cosmic Morse code tapping through the upper air. If you like wishes, keep a notebook by the lawn chair. Now zoom your imagination down to microscopic fallout. When the tiniest grains burn up high above us, they leave behind metal atoms and even smaller smoke-like particles that settle slowly through the middle atmosphere. Those specks can act as seeds for unusual, high-altitude icy clouds that glow right after sunset in polar summer. The delicate noctilucent veils that look like silk brushed with moonlight. A richer supply of dust could nudge those displays to be a little more frequent or a touch brighter one season, an elegant, indirect echo of a traveler long gone. Move outward to our airless neighbors. Bodies like the Moon and Mercury live inside a perpetual shower of micrometeoroids. They lack thick air to slow the grains, so the surface takes the hits directly. Each tiny strike kicks a puff of atoms off the ground, breathing a whisper-thin exosphere. If the dust river briefly thickened, those puffs would come a little more often. You and I would not notice from a backyard, but instruments sniffing the space around those worlds could record a change in trace gases, a spike in the fragile, short-lived atmosphere that hovers a hair above the surface. It is like tapping ash off a campfire, stick a little more often than usual. The traveler also releases gas, water vapor, carbon dioxide, and other volatiles that boil away in sunlight. In the vacuum of space, these gases do not linger as clouds you can point to, but they do become part of the solar wind's cargo as charged particles once sunlight strips electrons away. Scientists call these pickup ions, and they behave like hitchhikers that suddenly join the great outward flow. A stronger than expected release would slightly alter the chemical fingerprints measured by instruments that taste the wind between the sun and earth. It is not a gale, not even a gust, more like a subtle change in spice that sharp-nosed chefs with the right tools could pick out. Closer to the sun, the traveler's dust could briefly thicken the broad inner ring of grains that spiral inward over time. That could make the inner heliosphere a fancy term for the sun's neighborhood, just a touch more reflective in infrared light. Spacecraft that map the diffuse glow would log the change and then watch it relax as grains are vaporized, swept away, or migrated inward and consumed. Think of it as a soft, dimmer switch turned a notch, then slowly clicked back, Could a heavy dusting build a temporary ring around the sun? Not in the neat Saturn photograph way, but the inner system already hosts wide, faint rings of dust aligned with planetary orbits. A generous traveler could enrich a filament here or there, a thread barely visible to the best instruments. It would be a cartographer's delight more than a tourist's selfie. A new contour line on maps of sunlight scattered by dust. There is also the museum value of fresh material. Those grains carry stories in their structure, how porous they are, how they respond to light, how they charge up in solar radiation. When a stream passes near Earth, sample collectors on high-altitude aircraft and dust sensors on some spacecraft can catch a few. Under electron microscopes, the grains reveal textures and chemistry that hint at their birthplace and the conditions in their nursery. It is like finding a note written in a dialect you almost recognize, with just enough odd phrasing to make you rethink the region it came from. Could a richer dust and gas season cause trouble for people on the ground? Not really. The effects live in the sky's faintest layers, or across the vacuum between worlds. Ships do not launch evacuation drills because a comet wore a fluffy jacket. The practical considerations belong to the observers and the instruments. Calibrations, adjusted for a touch of extra glow. Filters chosen to tease out weak emissions from exotic molecules in the traveler's halo. And radio operators noting brief, graceful meteor pings on their charts. Culturally, there is a quiet beauty to this scenario. The visitor passes. The headlines cool, yet for months, subtle signatures ripple through the inner system. A slightly brighter zodiacal wedge, a surprise outburst from a newborn meteor shower. A few more nights when polar twilight wears silver lace. It is like hosting a guest who leaves behind a stack of postcards in the hallway mirror. You find new ones as you head out the door, each with a grain of story. And that is the core of this what if. A generous delivery of dust and gas would not rewrite the rules of our neighborhood, but it would underline passages we often skim. The inner system is not empty. It is a living archive of small things moving in great light. A traveler who sheds a little more than expected would not make the sun misbehave or the ground tremble. It would make the background audible for a while, soft, intricate, and worth leaning in to hear. Chapter 13, What If 3? Subtle resonances and long rhythms. Resonance is the universe's way of rewarding punctuality. Give a system small nudges at just the right times, and tiny pushes add up into big choreography. A swing in a playground proves the point. Tap it in rhythm and it soars. Tap it off beat and it sulks. In space, rhythm becomes architecture. Moons lock into step. Rings carve themselves into lanes, and asteroids gather in quiet traffic jams where the timing feels just right. The question for our visiting interstellar traveler is simple. Could a one-time guest whisper into any of those long rhythms and make a lasting change? To answer that, we need a clear picture of what resonance actually demands. First, it wants a repeating schedule. Bodies must pass the same places with clock-like regularity, so that gentle tugs align rather than cancel out. Second, it wants a way to keep time, a physical connection that carries the beat from one pass to the next, usually gravity, but sometimes light and heat for very small objects. Third, it likes patience. The build-up is slow and steady, more metronome than drum solo. Look around the solar system and you see resonant craftwork everywhere. 3 of Jupiter's large moons keep a set of linked rhythms, where one completes one lap, the next completes 2, and the third completes 4, with their alignments repeating like a waltz. Neptune shepherds a crowd of asteroids that share its year length in a tidy pattern, each safely ahead of or behind the planet, because the timing keeps them out of trouble. Even dust can get caught bunching into soft rings held in place by repeated nudges with a planet's path. These are not coincidences. They are the footprints of long conversations. Could our traveler join one of those conversations? In the usual case, no, because it is not staying for the after party. An interstellar visitor on a one-way arc does not return to the same places on a schedule. Without repeat visits, there is nothing to stack. One whisper is just that, a whisper. The swing forgets one off-beat, tap the moment it fades. But speculative does not mean careless. So let us sketch a narrow set of only-if paths. One possibility is temporary capture. If the traveler were to pass just so near a giant planet, losing a sliver of speed in a way that turns a one-way arc into a stretched loop, it could linger for a while. Celestial mechanics calls these windows keyholes because they are tiny and precise. Slip through, and the door to a longer stay opens. During that longer stay, the newcomer might pass near the same planets repeatedly and begin to feel the steadying hand of resonance. Even then, the capture would likely be brief in cosmic terms, perhaps a few loops before the object is escorted back out. Another possibility is not the traveler itself, but what it leaves behind. If the nucleus sheds fragments that end up in bound paths, those pieces could be gently herded by the clockwork of the planets. Over years, small grains drift under sunlight pressure and thermal forces, slowly changing their paths until some become trapped in gentle relationships with a planet's year length. The result could be a faint, temporary enhancement of an existing dust lane, a slightly thicker thread in the broad fabric of the inner system. Think of a seed caught in a slow river eddy, swirling for a season before slipping away. You could also imagine a resonance that is not about position, but about spin. Small, irregular fragments can have their rotation altered by sunlight itself. Over many months and years, an uneven surface that warms in daylight and cools at night can experience a tiny push that speeds or slows the spin. If a fragment were large enough to survive, but small enough to feel this effect strongly, it might drift toward a rotational rhythm that lines up with regular heating and cooling cycles along its path. That would not move a planet or stir the sun, but it would quietly sculpt the lives of pebbles and boulders birthed from the traveler. What about very long rhythms on Earth, the kind that slowly tilt seasons or shuffle climate patterns over tens of thousands of years? Those are set by deep relationships among our planet's path, its tilt, and slow wobbles in orientation. To nudge those, you would need repeated, well-aimed gravitational encouragement across ages. A quick guess does not qualify. It would be like trying to alter the length of a symphony by tapping your pen during one bar. The orchestra keeps its score. There is a more poetic angle to resonance that is worth keeping. Even when a newcomer cannot join the dance, it can help us hear the music better. If the visitor's dust briefly brightens the soft glow near the plane of the planets, instruments that map that glow can trace the hidden rings and waves carved by long-standing resonances with greater clarity. In that sense, the traveler is not composing a new rhythm, but turning up the lights on the hall where the old ones are playing. Scientists love these accidental spotlights because they let us refine maps of where dust lingers, how it drifts, and how planets quietly shepherd the smallest citizens of the solar system. Now for the guardrails. When people hear the word resonance, they sometimes imagine a fragile system one note away from breaking. In reality, celestial resonances are usually stabilizers, not triggers for chaos. They keep worlds from colliding, they separate rings into lanes, and they give small bodies safe harbors. If a new object somehow slipped into such a relationship, the likely outcome would be gentle guidance, not sudden fireworks. The cosmos is more careful gardener than reckless DJ, so the verdict for this what if is measured. A single pass does not conduct the symphony. Resonances thrive on repetition, and a one-time traveler does not bring a clock. Only in rare, sharply defined circumstances, temporary capture, bound fragments, dust that drifts into existing planetary patterns, could the visitor leave a resonant fingerprint, and even then, the mark would be subtle and patient. That does not make the story dull. It makes it musical in a quieter key. Resonance is the art of time, and time asks for many encores. A guest who bows only once leaves the melody unchanged. But sometimes the audience leans in and for a while hears the score with new appreciation. Chapter 14, Earth's Shield Systems, Atmosphere and Magnetic Field. If Earth were a castle, it would be a fortress with two superb defenses, a layered wall of air and an invisible force field, powered by the planet's heart. One blocks, filters, and softens what falls from space. The other grabs charged troublemakers by the collar and marches them away from the front gate. Together, they turn a harsh, cosmic neighborhood into a home address. Philona Ravenshaw. Earth is basically a rock that won the cosmic lottery. These two shields are the fine print that made the winnings spendable. Start with the wall of air. Our atmosphere is not a single blanket. It is a stack of distinct rooms, each with a job description. Closest to the ground is the everyday weather room, where clouds patrol and birds file flight plans. Above that sits a calmer, layered hall that stores a precious sunscreen called the ozone layer. Higher up is a colder, darker chamber where most incoming specks of space dust meet their fiery retirement party. Climb again, and you reach a region that warms under hard sunlight and thins toward the edge of space, where air becomes so sparse that a fast molecule can wander off and never come back. Each room weakens a different kind of incoming hazard. Ultraviolet light is trimmed, energetic particles are slowed, and small stones are cooked into harmless stardust streaks before they ever audition for a role as ground clutter. That last point is easy to miss because meteor shows are beautiful. We cheer the bright streak and forget what it means. The atmosphere just turned a tiny space pebble into a safe painting in the sky. Without that high-altitude burn zone, small projectiles would pepper the ground every night. The air column above you is not empty. It is a hard-working filter. It dims the harshest sunlight into life-friendly wavelengths, breaks apart many chemicals that would otherwise pile up, and spreads heat around the globe so nights are not Arctic on the equator, and days are not oven settings at the poles. Photosynthesis is plants saying they invented solar panels first, but they could not have opened that workshop without the atmosphere setting the light dial to gentle. Now the second defense, Earth's magnetic field. Picture electric currents swirling deep in the outer core, where liquid metal moves in vast, slow rivers, driven by heat from below and cooling from above. Those motions act like a planet-sized dynamo, weaving an immense magnetic field that threads outward through rock, sea, and sky. Charged particles from space care about magnetic fields the way fish care about currents. They are steered, guided, and trapped. Many incoming particles get turned aside, high above the ground. Others are corralled into long loops that keep them busy, far from where people live, work, and plug in their laptops. The field is a traffic cop with infinite patience. A favorite myth claims the magnetic field is fragile or about to vanish. The truth is more interesting. Earth's field has flipped direction many times across deep history, a graceful quirk recorded in the iron of ancient lava and in stripes spread across the ocean floor. During reversals, the field does not blink to zero and leave the planet naked. It becomes complex, with more than 2 poles before settling into a new arrangement. Life has cruised through many such episodes without a mass extinction alarm tied to magnetism alone. The field can change, but the shielding does not simply go on break. What about the famous weak zone over the South Atlantic, where satellites sometimes take extra care? That region is a dent in the field's armor, not a missing plate. High-flying hardware occasionally sees a little more radiation there and plans accordingly, the way you might slow down for potholes on a familiar road. On the ground, you would never notice. The air and the field still share the workload, and your body receives far more variation from long airplane flights and mountain vacations than from that distant quirk in the sky. The atmosphere and the magnetic field do not work in isolation. They are a tag team. Hard sunlight energizes the high air, building layers that can reflect radio waves and carry signals across oceans. The magnetic field funnels arriving, charged particles toward the polar skies, where they quietly hand their energy to the upper air. and paint those famous curtains of color. The show is a side effect of protection. It is the castle's watchtowers glowing during a well-handled drill. If you want a sense of what these systems do for us, compare Earth with our two nearest planetary neighbors. Mars had volcanic warmth and flowing water long ago, but without a global magnetic field to deflect the star's charged wind, the upper air was slowly shaved away. The planet kept a thin wisp, but the cozy blanket is gone. Venus took a different path. No global magnetic field, but a hugely thick atmosphere that acts as brute force armor against most incoming particles and stones, at the cost of a surface that would melt your lunchbox. Earth found the practical middle, a strong but breathable sky, plus a magnetic guardian that manages most of the charged traffic before it meets the air. The result is not luck alone. It is a layered strategy born from a churning core and a planet-sized climate machine. Even our technologies lean on these shields. Navigation satellites ride a careful balance of altitude so the thin upper air does not slow them too quickly, and so the charged particle environment does not age them too fast. Power grid operators pay attention when the magnetic environment gets a little lively, because long wires can pick up unwelcome currents. Airline routes sometimes shift away from polar skies during high activity, not because the planet is in danger, but because communication works better a little farther south. None of this is panic. It is housekeeping. The best part of this whole story is that our shields are not static museum pieces. They breathe with the sun, the seasons, and the slow churn of the deep interior. That breathing is not a weakness. It is health. A living atmosphere and a living magnetic field are signs of an active planet doing what active planets do: adapt, mitigate, and protect. Black holes may be the universe's way of deleting browsing history permanently, but Earth's shield systems are the browser extensions that keep pop-ups from crashing the page. So when headlines claim a visitor might flip a cosmic switch and put our world at risk, remember the castle. The walls are layered, the gatekeepers are stubborn, and the heart of the fortress powers a shield that does not frighten easily. Wonder at the sky, take the photos, enjoy the auroras, but rest easy. The defenses are old, clever, and very much awake. Chapter 15, Preparedness over Panic. What truly helps people on the ground. When headlines get loud, the smartest move is not a sprint to the supermarket. It is a quiet check of your plan. Preparedness is not a bunker vibe. It is everyday competence with a dash of neighborly teamwork. Think of it like seatbelts for life. You hope not to need them, but you click in before the road gets bumpy. Panic is loud and short. Preparedness is calm and durable. Start with the one thing that beats rumors every time. A simple, written playbook, not a novel. One page, who you call first, where you meet if phones fail, which friend outside your area agrees to be the message hub. Put copies on the fridge, in wallets, and in a photo on every phone. During confusion, people do not rise to the occasion. They fall to their level of practice. A small plan you actually use is better than a big plan you never finish. Home readiness is not about buying everything. It is about removing single points of failure. Water is first chair. Store enough sealed drinking water for several days for each person and pet. Add a filter or purification tablets so you can refill cleanly if taps sputter. Food is second chair. Choose shelf-stable items you already eat so you can rotate them during normal life. A hand-powered can opener has saved more dinners than any fancy gadget. Energy comes next. Flashlights with spare batteries, a small battery bank for phones, and if your budget allows, a modest solar charger. Paper maps and a small radio feel old school until towers drop, then they feel like magic. Secure your space. Heavy furniture and tall bookshelves should be anchored to studs. TVs like to leap, so strap or brace them. In the kitchen, install simple latches on upper cabinets so dishes do not become confetti. Know where the gas and water shutoffs are and keep the right tool nearby. Label the breaker box. In a power loss, flip the main breaker before the neighborhood comes alive again. It protects appliances from an unruly surge. Now for the go bag. Think one backpack per adult that you can grab in a single motion. Inside, copies of key documents, a small first aid kit, basic medications with a written list of doses, a change of clothes, a warm layer, a compact rain layer, a headlamp, some cash in small bills, and simple comfort items for children. Add pet supplies if you have animal family members. Pack shoes near the bed, so a midnight scramble does not become a barefoot obstacle course. Workplaces matter too. Keep a small kit in your desk: water, snacks, a flashlight, a whistle, and a phone charger. Walk your exits once a month, not because you're anxious, but because your feet remember routes better than your eyes do. If you manage a team, practice a 90-second drill. Who grabs the first aid kit? Who checks the nearest restrooms, where the outdoor rally point is? Short, regular drills beat annual mega drills because people actually learn them. Information hygiene is its own form of safety. Pick 2 or 3 trusted sources before a crisis. Bookmark them, and ignore screenshots that appear without links or dates. If a message demands that you forward it right now to save the world, pause. Genuine alerts rarely beg for virality. Adopt the kitchen rule. If you would not serve it to a friend without checking the label, do not serve it in your group chat. For earthquakes specifically, practice the simple trio: drop, cover, and hold on. Get under a sturdy table or desk, protect your head and neck, and stay put until the shaking stops. Doorways are not safer unless they have a modern frame and a door you can actually brace. Most are just skinny hallways with a splinter plan. After the first jolt, expect follow-ups. Put on shoes, check for gas smells and obvious damage, text instead of calling to leave lines open, and check on neighbors who might need help. Elevators are for calm days. Take the stairs after a significant shake. For power and communication outages, think in layers. Your phone is the first layer, but it is fragile. The second layer is that battery bank and radio. The third is a neighborhood bulletin board or a simple chalkboard in a shared space. Communities that agree on a single physical posting spot recover faster because information stops scattering like confetti. Consider a block-level phone tree that you refresh each season. 5 calls per person beats 1 overwhelmed organizer. Medical readiness is about the boring basics. Take a first aid class. Learn how to stop bleeding, how to use an epinephrine auto-injector if someone nearby carries one, and how to recognize signs of stroke and heart trouble. Keep an extra pair of prescription glasses in your go bag if you need them to function. If you rely on powered medical devices, talk with your doctor and utility company about priority lists and backup power options. A small planning call on a sunny afternoon can be worth 1,000 candles during a storm. Transportation is part of preparedness. Keep the fuel tank above half during risky seasons. If you rely on public transit, print or store offline versions of key routes and have an alternate path that you can walk. Shoes beat style in a real exit. Stash a small kit in your car: water, blanket, flashlight, reflective triangle, and a paper copy of important numbers. A dead phone is far less dramatic when your glove box knows who to call. Community is the secret ingredient. Meet your neighbors before you need them. A simple weekend coffee can reveal who has a generator, who is a nurse, who has mobility needs, and who speaks multiple languages for translating official notices. Organize a small skill swap. One person teaches basic fire extinguisher use. Another shows how to shut off utilities. A third reviews pet evacuation tips. When people have a role, fear has less room. Digital life deserves a seat at the table. Back up important files using the simple rule of 3. 1 main copy, 1 local backup, 1 offsite or cloud backup. Write down passwords for critical accounts and store them in a sealed envelope with your documents. During chaotic moments, no one wants to play guess the login while the flashlight is dimming. Finally, the mindset. Curiosity and calm are better than dread. Practice short breaths and a quick body scan when alarms go off. Feet on the ground, shoulders down. jaw unclenched. Give yourself one sentence that you can say out loud. I know my plan. I will do the next right thing. Humor helps too. Think of preparedness as the world's least glamorous superpower. You will not look like a comic book hero. You will look like the person who brought spare batteries and snacks. In a crisis, that is exactly who everyone wants nearby. Preparedness is not fear dressed up. It is confidence, rehearsed. Make the plan, anchor the shelves, pack the bag, know the exits, meet the neighbors. When noise rises, you will not need to sprint for answers. You will already have them, folded in your pocket, ready to use. Chapter 16. Why interstellar visitors matter. Anyway, every so often, the sky delivers a traveler with no return ticket, an object that does not belong to our solar family, gliding in from somewhere else and heading back out again. It is tempting to treat these passers-by as curiosities, like a rare bird that swoops over your backyard and vanishes. But interstellar visitors are more than pretty sightings. They are field notes from other star systems, written on stone and ice. When one appears, it quietly offers answers to questions we have been asking for decades, and asks a few bold new ones in return. First, they are unbiased samples. Most of what we study in the solar system grew up in the same neighborhood and carries the same family accent. Interstellar visitors were born under different suns, stirred by different giant planets, and aged in different radiation baths. That means their surfaces, interiors, and dust grains preserve a history that does not mirror our own. Even a short spectroscopic look, light split into its fingerprints, can tell us whether the recipes used to build small bodies elsewhere match the ones at home or diverge in surprising ways. If they match, that hints at common rules for planet formation across the galaxy. If they differ, that hints at a wider menu of planetary kitchens than we imagined. Second, they calibrate our models. Planetary scientists run vast numerical experiments to understand how young systems work, where giant planets migrate, how small objects are scattered, and how often some of those objects are thrown completely out. The rate at which we detect interstellar visitors helps set the dial on those models. Too few detections would mean ejections are rare. More frequent detections suggest that many newborn systems toss material freely into the dark between stars. Each traveler we log is a vote in that cosmic census. Third, they stress test our telescopes and teamwork. Visitors arrive without much warning and move fast. Catching them well requires rapid coordination between survey cameras that discover them, big observatories that dissect their light, and smaller community instruments that can cover gaps in time and geography. Every successful campaign builds our muscles for the next surprise, whether that is a strange comet, an outburst on a distant world, or a near-Earth object we want to characterize quickly and calmly. In that sense, each interstellar target is also a drill that makes the entire observing ecosystem sturdier. Fourth, they are laboratories for surface physics in unfamiliar conditions. A body that has wandered the deep cold between stars for ages may carry fragile structures on its skin, crumbly layers, strange crusts, or trapped gases that respond to sunlight in unusual ways. As the visitor warms, outgassing can change its spin, shed fragments, or sculpt jets that flicker in hours rather than months. Watching these changes teaches us how small bodies breathe, crack, and evolve when they wake from long hibernation. The lesson does not only apply to interstellar objects, it sharpens our understanding of local comets, asteroid surfaces, and even the dust that threads the inner solar system. Fifth, they provoke healthy speculation about life's raw materials. No, this is not the part where a single comet seeds a planet like a gardener with a watering can, but organic building blocks and other prebiotic ingredients do hitch rides on small bodies. If many star systems eject such material into the spaces between them, then the galaxy may be trading starter kits for chemistry all the time. That does not declare life common or rare. It simply widens the distribution channels for the ingredients. Think of it as the difference between one bakery on one street and a network of bakeries all exchanging flowers and spices. The menu possibilities grow. Sixth, they inspire new mission ideas. A known bound comet lets us plan a rendezvous years ahead. An interstellar visitor is more like a sprint. That challenge has sparked concepts for interceptor spacecraft waiting in a parking orbit, fueled and ready to dash the moment a promising object is found. The payoff would be immense. Close images, in situ dust analysis, perhaps even a fly-through of a fresh debris plume. A single successful intercept would move us from informed guesses to direct evidence about materials forged under another star. Seventh, they connect science with the public in a uniquely honest way. A visitor from beyond our system invites a simple, joyful sentence. This rock is from somewhere else. That clarity cuts through jargon. It turns evening sidewalks into impromptu classrooms and makes children ask the best kind of question: where is its home? Outreach is not a sideshow. It is part of the reason we do astronomy at all. The more people see themselves in the long story of the sky, the more they support careful, sustained work that carries no instant payoff but yields deep dividends later. Eighth, they reveal the quiet structure of our own backyard. A visitor's dust can slightly brighten the soft glow along the planetary plane, and for a time outline the faint rings and waves that already exist there. Instruments use those moments to map subtle features that are otherwise hard to see, much as a low sun angle highlights footprints that noon light erases. In this way, outsiders help us notice insiders. Ninth, they remind us to keep our tools tidy. Rapid follow-up demands accurate orbit solvers, well-curated data archives, and open pipelines that other teams can audit and reuse. Each campaign exposes bottlenecks and biases we would otherwise miss. The next discovery, whatever its nature, benefits directly from those quiet infrastructure fixes. Finally, they keep wonder honest. A traveler from another system is dramatic enough without extra myth. It asks us to hold two truths at once. The universe is full of ordinary physics, and that ordinary physics produces sights so strange and beautiful that we do not need to embellish them. Interstellar visitors matter because they are proof that our solar system is not an island. We live on one shore of a vast archipelago of worlds. Every time a messenger skims our harbor, we glimpse the outline of a coastline we have not walked yet. So when a new object appears on the survey feed and astronomers start rearranging their nights, it is not only about one visitor. It is about tuning our ears to the wider chorus, testing our readiness, and adding one more line to the story of how planets are made, how they change, and how their small, stubborn remnants carry the memories of their birthplaces across the long, dark. That is why it matters, because each arrival is a postcard from the rest of the galaxy, stamped with a place we have not met, and signed simply, "Wish you were here." Chapter 17, The Joy of Not Knowing Yet. How uncertainty moves science forward. There is a delicious moment in every real discovery story when someone leans back from the data and says, "I do not know yet." That pause is not defeat, it is the starter pistol. Uncertainty is not the enemy of science. It is the oxygen it breathes. Without room for doubt, we would have no room for better questions, no motive to build sharper instruments, and no reason to check whether the universe is trolling us with a clever illusion. If certainty were cheap, curiosity would retire. Science treats knowledge like a campsite. You leave it tidier than you found it, but you expect the map to be incomplete. The most honest papers carry careful caveats, because the authors know that future readers will bring better flashlights. This is why you will often see phrases like consistent with, within the limits of, or we cannot rule out. Those are not hedges, they are signposts. They tell you where the ground is solid and where it might still be quicksand. A result without uncertainty is like a selfie without context. Flattering, maybe, but you have no idea who was holding the camera. Uncertainty also keeps us humble about our tools. Every detector has a personality. Some are noisy, some are moody, some drift if you ignore them. Calibrations are the pep talks we give our machines before sending them back into the field. When we measure the same thing in two different ways and get slightly different answers, that is not an embarrassment, at least not immediately. It is a clue that helps us learn which method blinks under pressure. The lab bench is part courtroom, part comedy club, your experiment is on trial, and the punchlines arrive when you discover the cable you thought was secure had been quietly unplugged since Tuesday. Doubt is also the antidote to pattern fever. Our brains love a tidy story arc. The sun rises, a signal spikes, a headline rhymes, and suddenly the universe is delivering poetry on command. Uncertainty interrupts that rush. It asks for a control group. It asks for a timeline laid out before we peak. It asks whether the same analysis would discover the same miracle if we shuffled the dates. In other words, uncertainty is the friend who takes your car keys when you are about to drive home on confidence alone. A healthy research culture makes uncertainty a team sport. One lab's gorgeous curve is another lab's hold on a second. Peer review, for all its flaws, is the spa day your ideas did not ask for but probably need. Reviewers exfoliate hype, trim loose claims, and send the manuscript back, wearing sensible shoes. The point is not humiliation, it is survival. Findings that endure after strangers poke them with every available stick are the findings that deserve to graduate from maybe to probably. Some of the greatest leaps in understanding began as misfits that would not sit politely inside the expected box. A planet wobbled in a way that screamed, "Something else is tugging me." A spectrum line refused to land where the old theories said it should. A detector clicked when the sky should have been quiet. Those jolts did not demand instant belief. They demanded patience and replication. Mystery is fun, but it is not a license. The grown-up joy is in chasing the mystery with enough discipline that if it evaporates, you still learn something true about your tools, your methods, or your assumptions. This is why negative results deserve better press. When a careful test finds nothing where a rumor promised fireworks, that is not a boring story, it is a map correction. It tells future explorers where not to waste their nights and grants them time for more promising trails. In a just world, null findings would get as many likes as dramatic ones because they spare the community from chasing mirages. Think of them as silent guardians of everyone's schedule and sanity. Uncertainty even shapes how we talk to each other. Good communicators resist the lure of the thunderclap and aim for the weather report. They will tell you what is likely, what is possible, and what would change their minds. They explain what would count as a real signal and what would count as noise wearing a sequin jacket. They also admit when a question is not ripe yet. That is not hedging, that is respect for the audience. The quickest way to lose trust is to pretend that every whisper is a symphony. There is also a psychological gift in loving the unknown. It frees you from the pressure to win every argument. You do not have to be the person who always has the punchline. You get to be the person who asks the next good question. That mindset encourages collaboration because colleagues become allies in a shared puzzle rather than opponents in a trivia night. Better yet, it invites newcomers. A field that celebrates, "I do not know yet," makes room for fresh eyes, which is often how the next breakthrough sneaks in. Uncertainty guides investment too. When we admit what we do not know, we can design instruments that actually target the gap instead of building shinier versions of tools that already answered yesterday's problems. Roadmaps improve when they include the fog. Agencies and universities make wiser bets when the proposals tell them plainly which assumptions could sink the whole boat and how the team plans to test those first. Crucially, uncertainty does not mean indecision. It means staging your confidence. You can act on high probability while still investigating low probability. Pilots do this, doctors do this, engineers do this. Science does it by ranking hypotheses, running the best tests first, and updating the ranks as results arrive. The bravest moment is not when a team stakes a claim. It is when they publicly change their minds. because new evidence dragged them to a better place. Science is the only sport where switching teams mid-game is a power move, not a betrayal. For the rest of us, uncertainty can be an everyday skill. When you read a hot claim, ask for the pathway, the timeline, and the controls. When you see a dramatic image, ask what would have looked different if the story were false. When you hear a confident voice, listen for the sentence that begins, "Here is what would change my conclusion." That sentence is the warranty. In the end, the joy of not knowing yet is the joy of being in motion. It is the feeling of standing on a shoreline before dawn, watching for a shape on the horizon that might be a ship or a cloud, or the first hint of an island we suspected but never charted. The sky will brighten either way, but the lookout who cherishes uncertainty will notice more, prepare better, and welcome the surprise without panic. Curiosity gets you to the water. Doubt teaches you how to sail. Chapter 18, Final Verdict and Wonder. Grounded answer. Bigger curiosity. Time to land the ship. We asked whether a visiting interstellar object could rattle our star and set our ground trembling. We walked through how the sun makes its own weather, how gravity respects distance, how the oceans would daub in any secret puppeteer, how space storms really work, and how to test a bold claim without fooling ourselves. After all that, what is the sober answer, and what should we do with the wonder that remains? Here is the verdict in plain words. A one-off traveler sweeping through the solar neighborhood does not have the means to rewrite the sun's mood or yank Earth's faults. The star's activity is driven from within by churning layers and tangled magnetism. Earthquakes spring from stored strain along crustal boundaries, not from passing strangers in the sky. If a newcomer were exerting a meaningful pull, our oceans would show it with a new and obvious rhythm. They have not. If a newcomer were sparking solar fireworks, multiple instruments would light up with a distinctive, repeatable pattern that tracks the visitor's path. They have not. The simplest story wins. The sun conducts its own orchestra. The ground moves to deep tectonic beats. That grounded answer does not shrink the mystery of an interstellar guest. It clarifies it. Instead of being a cosmic switch we should fear, a traveler is a rare sample we should study. Its value is not in imagined superpowers, but in the quiet facts it carries, the mix of ices, the grains it sheds, the way sunlight sculpts its surface during a brief warm season. Think of it like a message in a bottle that washed onto our shore. The point is not that the bottle drifts our tides. The point is that the note inside tells us how distant coasts build their worlds. There is a useful habit to keep after the headlines fade. When a dramatic claim appears, ask 3 questions. First, what pathway would make this physically possible? Second, what timeline and measurements would prove or disprove it? Third, what would count as a fair control? If those answers are vague while the story is loud, your skepticism is doing its job. Curiosity is a flashlight. Skepticism is the extra battery in your pocket. So what remains to be excited about? Plenty. Interstellar visitors let us test ideas about how young star systems eject debris, how often such debris wanders the gaps between suns, and whether the chemistry of distant nurseries echoes our own. They motivate interceptor mission concepts that would wait in deep space for the next sprint opportunity. They sharpen our instruments and our coordination because catching a fast mover demands nimble teamwork across observatories and time zones. They even help us map the faint dust architecture of our own backyard when their crumbs subtly brighten the planetary plane. There is also the human side. A bright visitor turns sidewalks into star parties. Strangers point upward and become less strange. Teachers get easy hooks for real science. Light split into fingerprints, orbits reconstructed from dots, instruments that listen for the faintest whispers. The night sky becomes a shared classroom with no tuition. Wonder is the gateway drug to patience, and patience is the gateway to understanding. If you want a personal takeaway, make it this. Let awe lead you to method. Enjoy the spectacle, then look for the quiet signatures that separate a story from a storybook. When someone insists a new object is secretly steering events, ask for the calendar and the mechanism. When they deliver only coincidences, smile and keep your telescope time for better targets. Calm is a superpower. It is also contagious, a small nudge for creators and communicators. We do not need to inflate the sky to make it interesting. A traveler from another system is already extraordinary without sprouting capes. Tell the truth well. How we measure, how we know, what we still do not know, and the audience will lean in. People can handle nuance. In fact, they crave it. The best twist in any science story is not that the universe breaks its own rules. It is that the rules followed faithfully produce sights so strange that they feel like myths made real. What about the next steps? Keep an eye on reputable forecasts for space weather. They matter for pilots, grid operators, satellite teams, and aurora chasers. Support survey projects that scan the sky every night. They're the reason we catch these messengers at all. Celebrate null results when careful tests find nothing, where rumor promised thunder. Those results protect our attention for the questions that deserve it. And if a future object truly does something unexpected, the same disciplined playbook will catch it cleanly and quickly. Let us end where good science ends, with a wider horizon. The verdict here is steady. No hidden strings, no cosmic backdoor controlling our days. But the curiosity this traveler stirs is bigger than any debunk. It reminds us that our system is one port among many, that the galaxy trades small parcels between star families, and that every now and then one of those parcels drifts within reach. We read what we can, pass the bottle to the next pair of hands, and update the map. In other words, mystery responsibly. Hold wonder in one hand and evidence in the other. That is how you walk out under the night sky and feel both safe and thrilled, both grounded and wide open. The universe does not owe us certainty on demand. It offers something better, a never-ending supply of questions that, when pursued with care, turn into answers that deepen the questions again. That is the real magic trick, and it requires no special effects at all.